What I'd like to do now is just introduce you to the rules of expectation and variance. And before we do that, what I'm going to have to do is give you a precise definition of what the mean and variance are. So for the mean, on the left here, we have the equation for the entire population. In there, of course, we're integrating from negative infinity to positive infinity, and that gives us mu. Of course, we don't have the entire population as biologists, except in very rare circumstances. Instead, we have a sample. So we'll use the equation on the right. X bar is equal to the sum of all of the individual observations divided by the number of observations. That's pretty straightforward. Below that, we have the equation for the variance, and on the left is the equation for the entire population, and on the right is the equation for the sample. One interesting thing, notice the equation for the mean and the variance and how similar they are. And in fact, we define the equation for the mean as being the first moment, and the equation for the variance being the second moment. So the mean is a measure of central tendency, and then the variance is a measure of dispersion. There are two other moments that we could look at. Those are the third and fourth moments, and those will tell us something about kurtosis and skew. We're not going to deal with those at this point. But there, the equations would look just like this, except that x of I would be cubed or to the fourth power. Now notice the equation on the right. Here we have s squared, so that's our standard deviation, right? And that's the sum of x of I minus x bar quantity squared divided by n minus 1. An important point I want to make here is that if we did not do it in this way, we would come up with an erroneous estimate. We have to standardize this somehow by the number of observations. Otherwise, as the sample size grew larger and larger and larger, if we didn't divide by n or n minus 1, then our estimate would become larger and larger and larger. So we're looking for an estimate that is going to stabilize around the true value. Now the reason we divide by n minus 1 instead of simply n is because we've done something here. In the numerator, you can see that we have x of I minus x bar. X bar, you know from the equation above, is our estimate of what the true mean is. So we're estimating a population parameter. And because we're estimating a population parameter, we have to pay a penalty, and that penalty is referred to as a degree of freedom. So we're losing 1 degree of freedom in the denominator here. So we have n minus 1 instead of n. So let's now look at begin with the rules of expectation. And the expectation operator is exactly what it sounds like. What do we expect the value to be? So here, c is a constant. What's the expected value of a constant? Well, if the constant is equal to 10, what do you expect the value of the constant to be? Well, we expect it to be 10. So the expected value of a constant is the constant itself. If we take that constant and multiply it times a random variable x, what is the expected value of the constant times the random variable x? Well, that's simply the constant times the expected value of the random variable x. So now, what is the random variable? What is the expected value of the random variable x? And if you think about it for just a moment, you realize, well, your best guess is going to be the mean, right? So the expected value of x is the same as the mean of that random variable x. What about if we add a constant to our random variable? So perhaps what we're doing is we have x, the random variable x might be body weights, and we're going to multiply everybody's body weight times 10. Maybe you're working on mice or something and it's easier to work with bigger numbers, so you multiply everything times 10. And then you want to scale the variable somehow, and you add 100 to it or something of that sort. Well, the expected value of k, which is a constant, plus c times the random variable x is simply going to be the constant plus the constant times the expected value of x. So it's just a linear operator. That's a nice property. And here, interestingly, the expected value of the sum of two random variables, so perhaps x is height and y is body weight or something of that sort, uh, the, the expected value of the sum of weight plus height is going to be equal to the expected value of weight plus the expected value of height. So the expected value of a sum is going to be the sum of the expected values. So that the expectation operator is pretty straightforward and simple. A little bit more interesting is going to be the variance operator. So here, if you think about it, where the variance operator is going to produce something just exactly like our equation for the variance from earlier. So the variance of a constant is 0. Well, of course, because a constant doesn't vary, so obviously the variance has to be 0. The variance, and this is perhaps the most instructive one, the variance of c times, so some constant times the random variable, is going to be c squared times the variance of that random variable. And if you go back and look at the equation for the variance, you'll see that that must be true. So here, that's an important point, and the reason this is important is this. If you have data, and in order to make your data easier to interpret or easier to look at, maybe all of your values are 0.001, 0.003, or something of that sort, and to make the numbers easier to think about and look at, you multiply everything times 100 or by 1,000 or something of that sort. And then you compute the variance of your transform variables, or your transform variable. Your variance estimate is going to be off by quite a bit. It is not going to be simply the variance of the random variable, it's going to be c squared. So if you multiply everything times 10, right, then the variance that you compute on the transform variables is going to be 100 times what the true variance is. So you need to guard against that both when you're reading papers and when you're writing your papers. If you're transforming your data in some way, you have to be careful about how you're presenting the variance if you report it, and depending on how you use it. Now, the variance of a constant plus a random variable is simply the variance of the random variable, because the constant, again, has no variance. The most interesting one, however, is going to be the next one, which is the variance of a sum of random variables. And this is critical. So imagine you have height and weight, and you're looking at the variance of the sum of a person's height and weight. And let's imagine that we're measuring those things in some sort of unique unit. It doesn't really make any difference. We can ignore the units. We're going to take the variance of the sum. Well, it's not simply the sum of the variances as it was with the expectation operator. Instead, it's the variance of x plus the variance of y plus twice the covariance of x and y. So the covariance of x and y is how those two variables covary. So if you're working on some metric in your data set and it's really the sum of two other random variables, and you're computing that, then your final estimate is going to be inflated by this covariance term if variance x and y are dependent on one another. If x and y are independent of one another, then the covariance term is going to be equal to 0. Now, in years past, I had my experimental design students prove this, this final rule of variance. We're going to skip through that. I will provide you with the proof if you want it, but it's a pretty intriguing proof, and it helps you understand the importance of this covariance term. So if the random variables are statistically independent of one another, that is, if they are orthogonal, then the variance of the sum is the sum of the variances. However, if they're not, if they're dependent in some way, if they are not orthogonal, then the variance of the sum is going to be the variance of one plus the variance of the second one plus twice the covariance. Now, if you have a constant in there as well, then that constant obviously is going to show up in the covariance term as well. So this final Rule of variance is the most important one, and we're going to come back to that when we start talking about analysis of variance designs. And in fact, we need all of these rules of expectation here when we start talking about our analysis of variance designs. All you have to do is keep these things in the back of your head, and at some point they will become second nature and you won't even have to worry about them. Terrific. See you next time.